All right, let's go ahead and build a phylogenetic tree. Now, as you can see, the first one, we have this table right here, which on the left-hand side we have all the characters. Okay, so here we have characters. We have backbone, hinge jaw, forelimbs, and amnion, milk, and dorsal fin. And then across here we have all of the taxa. Okay, so these are the ones we're going to compare. Now, normally the term outgroup is not going to be there for you, right? So that's really the first thing that you want to try to determine is what is your outgroup? Or really when you're building a tree and you're doing research, you're going to choose your outgroup, and you're going to choose your outgroup which may be closely related to your in-group, which is, remember, the rest, basically all the organisms that you're going to be comparing. It's going to be closely related, but not within that group normally. So normally that outgroup isn't going to have any of the characteristics that your in-group does. If it does have any, it's probably just one. All right, so let's kind of look at this asterisk right here. So this asterisk kind of points to this information down here. Okay, and it says, although adult dolphins have only two obvious limbs, they're flippers, as embryos, they have two hind limb buds for a total of four limbs. Okay, so here we have, we're going to say four limbs are present, but we're going to look at two different trees where we basically use the morphology of the adult dolphin and then look at the comparison of the tree if we used the fact that it does actually have four limbs during development. Now, what you want to do first is basically first you determine what your outgroup is, and then you're going to start to build the tree. Now, what I'm going to do is build it kind of like what your lab manual is asking. Okay, so with the lab manual, you're going to use cladistics, and you're going to basically draw a diagonal line. Okay, all of your branches are going to come off of that diagonal line. So we'll go ahead and put this as the ancestor of all of the groups of organisms, right? Including your outgroup. Now, your outgroup is going to be the first one to branch off. Now, it's always important to remember that the taxa belong at the ends of the branches, okay? The characteristics or the shared derived characters or traits are going to go basically be hash marks along the lines or lineages of your tree. Right, so we know what the outgroup is. The outgroup here, we're going to go ahead and have that branch off first, and that'll be the lancelet. Okay, the lancelet has 0 characters, so it's very closely related to the common ancestor of all of our groups of organisms. Now, the data in this table are organized very nicely. Now, if your data is not organized in this way, where you can kind of see a diagonal where the presence of traits starts to increase. Now, you might have some odd ones, which is totally fine. But it's a good way to organize your data in such a way that it makes it easy to read. So now you're going to look at your next organism. So now basically we know the lancelet has none of the traits. Right. Now, what happens which distinguishes the lancelet from something else that only has that one trait, right? So look, we've got the lamprey, which only has one trait. And what trait is that? It's a backbone, right? So we know, we could go back to the tree, that backbone happened first. Okay, so backbone happens. And then we have our next group that diverges, and that's going to be the lamprey. Oops. We have lamprey on our tree, and we're going to start moving the same way. So basically, you're going to use the same idea as we did before. So now we have the lamprey on there, and then we have tuna, which has 2 additional traits. And then we have salamander, which has, well, 2 additional, plus this one down here. And then the salamander, which has the 3 additional traits. And then what we want to do is try to determine where we want to put something next. So I'm thinking that the tuna will go next, right? because it has a hinged jaw. It also has a dorsal fin, right? Dolphin also has a dorsal fin. So we're going to kind of have to worry about that in just a moment, right? So let's go ahead and put tuna on there, right? Tuna. Okay, so tuna has a hinged jaw. So you can see that everything else has a hinged jaw. Now, tuna also has a dorsal fin, but only the dolphin has a dorsal fin. So you don't want to put dorsal fin here, because if you put it here, then that suggests everything after that also has a dorsal fin. Okay, so we know that everything has a hinged jaw. So we're going to put hinged jaw here. Okay. Now, tuna also has a dorsal fin, right? So let's go ahead and put dorsal fin here. Okay. And now we have salamander. Okay, so salamander has 4 limbs along with everything else. So we can put 4 limbs, which happen next. 4 limbs. Okay, and salamander is the first one that has 4 limbs but doesn't have any of the other characters that we're looking at. All right, so we have salamander here. All right, so what's next? We just kind of move on down. Look, the data is just perfect for us. So now we have an amnion. Everything else has an amnion. Right? So the next thing to branch off is going to be a turtle. All right. Then we have milk. Okay, so the leopard and the dolphin both produce milk. Right, so now we have a leopard. Okay, and then we have a dolphin that just kind of falls off the end here. All right. So what's different about the dolphin and the leopard, right? So the dolphin also has a dorsal fin. All right, so now look, we've got dorsal fin twice. But the dolphin has 4 limbs based on embryology, right? So we've got this tree. And let's remember, from the text, you should have read about the principle of parsimony. Okay, the principle of parsimony states that basically the simplest explanation is the best explanation. So when you were talking about trees, the simplest explanation would be the explanation or the hypothesis, in this case, since trees are a hypothesis, that requires the least amount of changes for it to be true, right? So we got how many changes here? We've got 1, 2, 3, 4, 5, 6, 7 changes. So we've got 7 events that must have happened for this hypothesis to be true. Now let's go ahead and build this tree again, except we're going to put the dolphin with the tuna as sister species, right? So we'll see what the difference in this tree will be, right? So let's go ahead and just start to draw the tree. I'm just going to quickly build it this time. Okay, so we have the lancelet. Okay, and then we have the lamprey. And then we have the tuna. And then we have sister species dolphin. And then we have the salamander. And then we have the turtle. And then the leopard. Okay, so let's put the events there. So this is the common ancestor of all of them. Okay, so the lamprey has a backbone, but the lancelet doesn't. All right, and then the tuna has the hinged jaw, but the lamprey doesn't. And everything else has hinged jaw. And then tuna and dolphin both have the dorsal fin. Okay, and then salamander has 4 limbs. All right, and then amnion, and then milk. Okay, so we've set this up, and we have tuna and dolphin as sister groups. Okay. Now, however, we need to add in some things regarding the dolphin because we know that the dolphin also has four limbs and an amnion. No, we're saying it doesn't have four limbs. Now we're saying it has an amnion and milk as well. All right, so now we have amnion and milk. Now, it actually does have four limbs, so we're going to go ahead and put four limbs here. And there's another way we could do this. We could put four limbs with the hen's jaw back here, and then put tuna no four limbs, right? So, but it makes more sense to do it this way. So let's count the amount of vents for this tree to actually be true. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 events, as opposed. Oh, I'm sorry, 7 events for this tree right here. So we have 7 events. So this one is the one that's most parsimonious. So if we did put dolphin with tuna, just because that they share this character, the dorsal fin, putting them as sister species, that would not be the most parsimonious way to do it. So this would be the best explanation or the best hypothesis to go with based on the data that we have. All right. So that's one example. I'm going to go ahead and post another one so you could go ahead and view that example as well.